Go. How's that?
There it is. Great.
Okay, wonderful. Thank you so much for that lovely introduction. I'm really happy to be here today to talk to you about something that is super important, and I think an emerging paradigm of conservation and climate solutions in the blue space, as we call it, or the ocean space. And I think it's a little bit of a mystery to some folks. So we're gonna have some fun talking about what blue carbon is, how the ocean is connected to our climate, and what some of these blue solutions might be. So without further ado, let me here get my advance going. I want to start with the bottom line, and we're going to end with the bottom line too. Well, we went past it pretty quickly. Give me a sec. We're going to start with the bottom line, which is that blue carbon ecosystems, and I'll end up defining what these are so you know what they are. They just store a lot of carbon, and this is one of their incredible properties, and why they're so important in the portfolio of climate solutions, if you will. So very important part of that new emerging understanding, and both in science and policy, that has allowed that to become the case. And in addition to being part of our portfolio of climate solutions, blue carbon ecosystems have many really important co-benefits for people and nature. So I would say those are the three bottom lines, take-home messages from this talk. But I'm going to tell you the story so that you can understand how important the ocean is, why it's different from the way we think about the green places on land that we know. So I have a storyline instead of an outline. So the first part of my story is going to be to tell you a little bit, and you probably know some of this already, about why the ocean is our planetary climate hero. And then I'm going to tell you some of the contradictions or differences between the big blue ocean beyond. It looks just very blue, but there's a lot going on there. And it's sometimes hard to see the trees for the forest, if you will, or what's going on underneath the ocean. And it's different. It's quite different from the green places we know well. So that has been part of the challenge of getting these blue climate solutions to be uptaken. I'm going to tell you a little bit about the story of ocean carbon, and it's a story of sources, sinks, and fluxes. And then we're gonna address how blue carbon, in addition to climate, obviously, is a really wicked problem, and how for scientists and policymakers, asking and answering the right question makes a huge difference. So there's a story about that in the blue carbon trajectory, if you will. I'm going to tell you a little bit about the new policies that are giving these blue carbon ecosystems their due. And then I'm going to end with a plea to account for for recognizing that we need to account for all that matters to address the climate crisis, not just the carbon. There are many other things that need to be addressed. And so that's kind of the arc of my story, if you will. So we'll start with the first part, which is the ocean is our planetary climate hero. And so for those of you who may not know what it is that the ocean's doing, hey ocean, what have you done for us lately? Well, the ocean would answer, it's way cooler than it would be without me. And I think most of you have probably are familiar with the statistics that the ocean has absorbed approximately 93% or so of the additional heat that has been put into the atmosphere from human activities. And this is just a graph. And the units are just kind of outrageous. Zettajoules. Have you heard of zettajoules? Not that many people have. So it's a big number. And you can see that it really dwarfs what's been absorbed or accumulated by land or atmosphere. And you can see how this has changed the heat, if you will, of the ocean over time, over the decades. This is just a nice infographic that shows that. Nice in the sense of a visual illustration, maybe not so great for the ocean. So it's way cooler than it would be. 93% of the additional heat, anthropogenic heat, since the 1970s. However, ocean is getting a little acidic in the process. I'm sure many of you have seen this is the famous or infamous Mauna Loa carbon dioxide plot. and series, but below it is also the corresponding plot of the carbon dioxide dissolved in the ocean. And you can see that it parallels the atmospheric trajectory pretty perfectly. And what happens, obviously, well, maybe not obviously, but what happens is that carbon dioxide in the water goes through a series of chemical reactions and ends up acidifying the oceans. This is a super fancy illustration of that impact throughout three major ocean basins: the Indian Ocean, the Atlantic Ocean, and the Pacific Ocean. The main thing that you need to take away from this graph is just those red areas on the right over here. These are the slices through the ocean from the top to the bottom, showing all this carbon dioxide accumulation in the upper levels of the ocean and the ensuing increase in acidity from that. So the ocean has captured about 26% of the CO2 emissions since 1750, and that has contributed to reducing additional warming, but it's acidifying the ocean in the process. And the heat the oceans absorbed means less ice melt from the atmospheric warming, but the seas are still rising. And as you know, sea level rise has been changing quite dramatically. We expect it to potentially accelerate. This is really problematic for all our coastal areas. It also presents some challenges for some of the blue carbon solutions, but thermal expansion and ice melt from land have contributed to about 8 inches of global sea level rise since the 1900s. So although the ocean has absorbed all that heat, there are some consequences for it. So the ocean is a buffer, but it does have consequences and limits. So heat, carbon dioxide, and holding of the water that's melting off of land. Big planetary ocean hero. So let's go a little bit into what are some of the interesting differences between the ocean and the greener places we know well on land, and what that means for carbon and carbon storage and carbon sinks. On the left, this graph, you can see, sort of a typical profile through the earth, where you have movement of carbon dioxide, photosynthetic uptake by plants and trees, and the formation of wood and soils, the contributions, obviously, of anthropogenic carbon, and then big carbon stores in soil, and some of the processes that contribute CO2 back into the atmosphere. Most of the carbon that's accumulating here is really accumulating up here in the upper biomass, long, deep storage over here, but on a day-to-day basis, it's going on here. In the ocean, what's different is the way that the carbon is being sequestered and taken up is through similar processes of photosynthesis and obviously some decomposition too, but there's this gigantic biological pump and microbial pump that is moving it into deep areas of sequestration. And it doesn't necessarily stay where it was produced. And that's kind of an interesting aspect. So the ocean covers about 70% of the planet, and it's powered, its productivity and its ability to do this movement of carbon from the atmosphere into the depths of the ocean and store it is powered by microscopic phytoplankton. These phytoplankton are as productive as land plants every year, even though they're tiny. They contribute at least half of the oxygen in our atmosphere. So a big energy, big machine there in terms of making biomass out of carbon dioxide. However, it's so different from the land. There's lots of plant biomass on land, but there isn't so much if you look at it in any given moment in the sea. It's because the production is turning over and being converted into animal biomass. This is just a graph showing you that the producers, which are the plants in a terrestrial setting, the biomass in gigatons of carbon, a snapshot of it is about 450 gigatons of carbon compared to the consumers. So that would be all the animals, including humans and lions and tigers and bears and deer and what have you. In the marine environment, in contrast, most of the biomass is held in the animals and in the consumers. Much less at any given moment, even though it's very productive, are in those plants. So that has consequences for the way we think about carbon stores and what it might mean also for connecting to climate policy and climate storage and sequestration in a way that really is going to make a difference for the planet. So I alluded to it, there's this biological pump that really moves a lot of this biomass down into the deep storage of the ocean. And so now I'm going to tell you a little bit about this story about where the sources, sinks, and fluxes are. And all three of these are really important in the ocean. The ocean holds nearly 50 times as much carbon as the atmosphere and almost 13 times as much carbon as the land. Most of it is in the form of inorganic carbon. You can see this number down here. This is also in gigatons of carbon, 37,000 in the form of dissolved inorganic carbon. All this, there's a budget that puts this all together, and a lot of data goes into it. There's a lot of uncertainty. These are big estimates, and there's a lot of measurements that need to be made to increase the certainty in it. But you can see that the dissolved inorganic carbon over here, 36,300 gigatons stored in this form. The dissolved organic carbon is much less, but that pool is pretty close. As a matter of fact, it exceeds the amount of carbon in the atmosphere. And you're going to see the next slide that this biology, the biological and microbial pumps, move carbon into deep storage. So storage below about 1,000 meters in the ocean. And the biological pump moves these particulate organic carbon, so the phytoplankton, the zooplankton, the small organisms in the ocean, into deep storage. And they can store it for hundreds to thousands of years in the form of particulate organic carbon. And it moves about, it's about 20 gigatons. And then some of that settles into the sediments, and there it can be stored for hundreds of millions of years, so substantial storage. The microbial pump is pretty interesting because that is the way that we get this huge pool of dissolved organic carbon. It's often called recalcitrant carbon, dissolved organic carbon, by the scientists who study it. And it sits in the deep ocean, and it is stored for over thousands of years. And there is going to be a connection to some of the coastal blue carbon I'm going to be talking about in a little bit with this recalcitrant DOC, as it's called by scientists for short. So I've talked to you now about things that happen on land, big carbon pools, processes on land, big carbon pools and processes in the ocean. And what we haven't talked about, which is the subject here of blue carbon, is sort of what happens in this narrow ribbon in between the ocean and the land. There is a lot going on there, more than is apparent, and a lot that matters for, all right. So if we zoom in, I'm not gonna, there's no test, there's no quiz. I just wanted you to show you that there have been a lot of folks working on getting the details of the carbon storage in this coastal zone. And the total carbon budget for North America was recently done by for the second state of the sort of carbon cycle of North America. And one of the things that you can see is that there's these significant fluxes between the atmosphere, the tidal wetlands, the estuaries, the rivers, and carbon is getting poured into storage in the wetlands, storage in the sediments, and off on the shelf waters too. But we want to focus on really this piece here and this piece here with the sediments for blue carbon. So blue carbon sequestration and storage is just like it happens on land. It's the uptake of photosynthesis, but it includes this unique component, unique to blue carbon, that is really the really important part is the storage in the soils. And of course, some is respired by the organisms, but small amount. Most of it is taken up in the soils. And there are many different blue carbon ecosystems. So these are habitats that are dominated by plants, and the three tend to be mangroves and tidal marshes and seagrasses. And we're going to talk a little bit about each one in turn. But tidal marshes are among the most important. And here's just a view sort of through the water, and you can see all the mud and the sediment at the base of those grasses there. This is a Spartina marsh. And they have sufficient extent to really be meaningful and to accumulate a lot of carbon, both through extension as sediment and biomass comes in and progradation out into the water area and the mudflats, but also by transgression and moving back up into the uplands. And here's a view of a marsh where there's some escarpment and sloughing off at the edge there to give you a sense of the depth of carbon that's stored and built up at these edges. And it turns out that this storage in the soil is the super important part. Mangrove ecosystems are another blue carbon ecosystem that do the same. They tend to be obviously more in the tropical areas, but you can see here that fringe of mangroves, the roots and the roots that come up, blanking for a minute on the term, not the pneumatophores, but the roots that come up to get the oxygen, they kind of poke up into the air too because of the anoxic sediments. And they also have an extraordinary extent at the coastal margin and store a tremendous amount of carbon. Seagrasses, the underwater gardens or meadows, right adjacent often to the mangroves and to the salt marshes in some cases, tidal marshes, also store an enormous amount of carbon. This is an eelgrass bed at low tide, so people can often get out, at least for part of those, but you can see another vast extent and some mangroves over there in the background. It also, if you can get a view of it, where there's some, this is an escarpment where you can see the accumulation in the sediment there. Some of them, especially the tropical ones, have a large accumulation also of calcium carbonate, and that's an interesting part of the story, but you get a sense of the depth here, very significant stores. And even though these ecosystems make up just the coastal fringe, about, maybe 2% of the ocean, of the surface of the ocean, they are distributed worldwide and they are powerhouses. If you want to get a sense of how much, the area specific carbon burial rate of tropical forests, boreal forests, and temperate forests are kind of really outdone on a per area basis by these salt marshes, mangroves, and seagrasses. And notice that this is a logarithmic scale. So these are exponential sort of jumps in those rates. Now, again, they occupy much less space, but at the end of the day, when you do the math, about 5 or 6 times as much sequestration in these systems, which is really extraordinary. But again, all of it is mostly in the soil. The organic carbon soil. So this is an example. You can see the brown part represents the soils, the green represents the living biomass, and if you compare that to a forest, you see that relationship is largely reversed. So key difference, very important. And these are the kinds of accountings that people do to figure out, the scientists do to figure this stuff out. They take a lot of data, they analyze it, pull it together. You need to understand the geographic extent, how much carbon is sequestered every year. And in a paper by Howard and Sutton Greer, colleagues who study this, they put together the carbon storage potential of these marine ecosystems. And they compared it not only the 3 that I just talked to you about, but they also looked at coral reefs and kelp and phytoplankton and fauna. And one of the things that's not in here is actually, this is an emerging area, is that the seaweeds, the kelps, may be another important blue carbon ecosystem. They didn't put them in here, but at around the same time, there was another publication that suggested that the sequestration value of seaweeds was between 61 and 268 million megagrams of carbon. And if you put that number in here, you can see it really rivals some of these other sequestration numbers. So it might even exceed some of the other blue carbon. So kelp forests have potential. You might go, wow, with numbers like that, why only potential? So, and I'm going to get to that because it's an important part of the story. But here you can see from an aerial view, these are kelp forests in Southern California. You can see the extent of them. There are kelp forests in many places around the world, including off the shores of Norway, Australia, just all over the place. So they are another very important part. And it turns out They are different, and this is why there's potential, and I'll get to exactly why from the policy and sort of carbon accounting perspective in a minute. But the way that they get sequestered, obviously kelps and seaweeds, they're attached to rocks. They don't develop the soil profile. Remember that I said was so important. What they do though, is that they get dislodged and transported and moved down deep into submarine canyons, and they get stored under the 1,000-meter mark. And that's where we have a carbon sequestration horizon for the ocean. And this is the number that's been estimated of how much of that kelp and seaweed that's on the rocky shores, what the potential carbon sequestration value of it. Actually, I shouldn't say potential, it is the value of it. Whether it's important for climate, blue carbon markets, and accounting is a different matter. But this is the mechanism. This is why it's a little different. And these are some photographs from off of Norway at depths at like 450 meters, starting to get close to that horizon off the fjords there, where they're just showing the state of the seaweeds and how they're not all broken down. They're still fairly intact and fairly big pieces when they get down into these sediments. So that's just sort of a related study that really demonstrates visually that this material is getting into those very deep places. And if you add the kelp forests, at least, and if you added seaweeds, it would have a similar distribution. But you add this, you can see that pretty much every shoreline is potentially important from a blue carbon perspective. All right, I alluded to some of these, the three sort of primary systems, the dependence on soil and accumulation of soils, the potential for kelp and seaweeds to be another blue carbon ecosystem. And now I want to tell you about why that is a potential and how these are kind of wicked problems from the science policy perspective. Climate is a wicked problem, but even trying to get an accounting of these coastal ecosystems, and even though they have all this carbon, how to get scientists to answer the right question is really important and helps with our work. So in the policy and science world right now, there are many practical considerations that need to be considered to be designated. This isn't a formal designation, but this is a designation folks are using to describe them for carbon markets and carbon accounting. To be designated as a blue carbon ecosystem, carbon sequestration or the emission of greenhouse gases, the prevention of the emission of greenhouse gases, those rates need to be sufficient in that ecosystem to have an influence on the climate system. In addition, we need to understand the major stocks, changes, and fluxes so that they can be quantified over space and time, because you need to know what bank to speak. The human drivers, the anthropogenic drivers, they have to be influencing these in some way for it to be meaningful in a policy and climate framework. The management of the ecosystem to improve sequestration or to reduce emissions also needs to be possible. Think about how we treat forests. And so deforestation, burning of forest, land conversion, all of those things play into this accounting on land. So similar principles would have to apply here. There need to be interventions that can be achieved without harm to people or the environment. So there are a variety of creative ideas that have been considered. For example, I'm thinking of the geoengineering and sprinkling iron all over the ocean so that it will enhance the biological or microbial, mostly the biological carbon pumps. And it turns out that, you know, that is not without its challenges, and we don't know that it would do no harm. The management actions, and this is the last thing that's super important, must be able to be aligned with existing or developing policies and commitments to address climate change. If we can't do that, we can't consider the value of these ecosystems effectively in that space. So those are some of the really important considerations. And you remember here I talked to you about how much of it was in soil. Well, it turns out that for a long time, most of the carbon accounting in terms of biomass accumulation ecosystem was really only accounting for carbon and biomass accumulating above the soil horizon. So this created a sort of a policy challenge, if you will. As I told you, most of this is being sequestered into the soils. What ended up being the really important thing to consider, though, also was not the rate at which these were accumulating carbon every year and into the soils, but asking a different question in the policy framework. This is what really got people's attention. What would be the greenhouse gas emissions if you destroyed these blue carbon habitats? And a lot of them were under threat and remain under threat. And it became super important to learn to ask and answer the right question. Scientists initially went in well-meaning to the policy space, to the climate space, and said, okay, look at how much carbon these ecosystems hold. They have to be important. You must take them into consideration. I mean, they really went in with this sort of naive, like, listen to the science, here's the facts, we're telling you it's important. And they went to the UN Framework Convention on Climate Change, COP16 in Cancun, and they were met with major skepticism. Their ideas were initially dismissed as not actionable. They went through a process of ongoing scientific collaboration and openness, though their optimism declined, and a lot more talking with the policy community. And it took a lot of talking past each other or in circles until they started to understand each other and started aligning. And what changed was they started to look at how much carbon or greenhouse gases would be emitted if these ecosystems were or are destroyed. And that changed the equation. Because they had the data on that. They just hadn't framed it that way. And that soil horizon, all that material there, you destroy the wetland, you start losing carbon. You start putting carbon and greenhouse gases into the environment. And it's a huge amount because it's been accumulated over thousands of years. And so finally in 2013, the IPCC issued a supplement that specifically addressed wetlands, that made it possible to include them in the national carbon inventories, which are the baselines for, for our agreements and carbon accounting, and provided the opportunity to consider them for the carbon markets. So, this is what we're talking about. What happens if you build up, dike, develop, fill all these wetlands, and they go away and they become urbanized areas, for example. Sometimes in the mangroves, they're destroying them for shrimp fisheries and other things. So, and the threat was real and are real. The global rates of loss of these ecosystems range from about 0.7 to 7% per year. That's about 3 to 19% of annual deforestation on land, and it's about equivalent to the total emissions of the United Kingdom. So significant if you lose that. So these new policies really gave blue carbon ecosystems their due in a lot of ways. And this document, this wonky document, became super important. And that's why we're starting to hear more now about blue carbon ecosystems, and they're starting to come into the carbon markets. So that document helps provide a basis for connecting the carbon and greenhouse gases into carbon pricing systems. You can connect it to emissions trading schemes, cap and trade, and carbon taxes. You can potentially get carbon credit or offset with tradable or sellable certificates for a right to emit 1 ton of carbon, right? You probably are familiar with these. There are also voluntary and compliance markets. Currently, blue carbon ecosystems are being used in the voluntary compliance market, but that's the precursor to entering into a fully compliant market where they would have more value. So right now there's a verified carbon standard that has been very useful in understanding the carbon. There are challenges, and certainly more science is needed. This doesn't stop. Science and policy, when science is informing policy and new questions come up or new challenges come up, this conversation just keeps going. And it's not to say that we don't know what we're doing as scientists, or that it's just that we don't have full information. We have a lot of information. Sometimes the application requires a different kind of information. So working together and bridging the gap and boundary spanning these spaces and being able to talk to each other is super important. Some of the challenges that we're seeing right now. Wetlands, for example, are super dependent in their ability to keep up with the march of sea level rise with sediment supply. And sediment has been in short supply in part because of damming in rivers and just some of the coastal armoring and various things that impede the supply of sediment. Under natural situation for quite a bit of sea level rise, the marshes can keep up, but sediment supplies become an important challenge. And there are policy things that can be done to address that to a degree. Another challenge are marine heat waves. We saw how much the ocean has been absorbing in heat, but we're starting to see heat waves pop up. And that has been really damaging. Here in Northern California, we've seen the challenges to our kelp forests that have been completely lost up to a large extent in Northern California. And a lot of work is going into figuring out how to restore them. And if you're gonna account for kelp going into the deep sea, you have to be able to, be fairly confident that the kelp is going to be there and it's not going to get destroyed. But there are a lot of places, both in federal and state policies, where we can put these two things together to do the accounting and get more investment in blue carbon, protecting blue carbon, and protecting the carbon that they're storing. So this is from a colleague, Ariana Sutton-Greer, and her work on a slide from one of her talks where she she did a policy analysis to try and understand what existing laws and acts and policies could be leveraged. And there are a lot of places where coastal blue carbon could be included. Clean Water Act, Natural Resources Damages Assessment, Coastal Zone Management Act, and the National Environmental Policy are all places where we could account for the carbon in these ecosystems. So carbon servers are not currently included in these, but they might lead to more habitat conservation and climate mitigation. And there are a couple of pilot projects that are good. One here in San Francisco Bay at Sears Point, and it's been leveraging a NEPA environmental assessment, and there's another example in a programmatic environmental impact statement. So these are important policy advances. In California, there has been a growing push both to restore and to protect existing blue carbon ecosystems. But in addition to that, they've been really thinking about how these ecosystems can also be used to manage ocean acidification in a local setting. So there's these other benefits to thinking about how these blue carbon ecosystems are working. And what I'd like to do at this point is close on this last piece, which is the carbon matters, but that's not all that matters in these blue carbon ecosystems. There's a lot to account for. And what I'd like to implore all of us to do when we think about these things is to account for all that matters to address the climate crisis. We can't look at these systems in isolation. These coastal ecosystems and those habitats that I've been describing, they provide an enormous number of services, some of which could be accounted for and valued in an economic context as well. We obviously, for those of us who love nature, including myself, who can't get enough of it, and we know now with COVID how much we value being able to be outdoors and get to our natural spaces, there's sort of this existential value of just having nature and being able to spend time in nature. But there are real benefits in addition to carbon storage. There's coastal buffering in the way that you get erosion and sedimentation and how those work together with the development of the marshes and the wetlands. Those ecosystems filter nutrients out, and we do need to manage our nutrient loading. They attenuate waves. Working with nature, there are lots of green, blue solutions to adapting to climate, to sea level rise, and some of the nuisance flooding that we're getting that's going to get worse. The cultural heritage is super important. The employment opportunities attendant on intact ecosystem, from recreation, tourism, talked about the enjoyment of nature, and simply in valuing and protecting biodiversity. All of these things contribute to our well-being and health. And I want to end by giving a plug also for the book of a couple of colleagues, Ayanna Johnson and Catherine Wilkinson. They just put together an anthology of writing in a volume called All We Can Save: Truth, Courage, and Solutions for the Climate Crisis. This book is good for your soul and will inspire you. I know this audience is inspired, but sometimes we need more than science. So I would encourage you to check out that book. It's just out. It's a wonderful, wonderful book. And I'm going to end again on those 3 bottom lines. The blue carbon ecosystems store a lot of carbon. They are definitely an emerging part of our climate solutions portfolio. And they have many important co-benefits for people and nature. So there are many, many reasons for us to care about, to conserve, to protect, to restore, and potentially afforest, plant more blue carbon ecosystems. And let's see. Is that my last? That might be my last slide. That's my last slide. I thought I had a thank you slide. Anyway, thank you very much for your attention, and I'd be delighted to take your questions. And I'm going to stop
Thank
sharing.
you, Karina.